Back to 7.2 with integration by parts. So this right here is the formula we proved in the last video. It is again the integral of u dv equals uv minus the integral of v du. And make sure that that actually is a v. It's got the tail horizontally where this has the tail vertically. So let's identify one more time. When is it that we're supposed to use this? We're supposed to use this when we have two clearly different functions multiplied together. One of them will be just a basic old function. The other one will be a part of that integral that absorbs that dx. So when we look down here, this is the first example we're going to play with. And in terms of this first example, you'll notice that we have two clearly different functions. One function is algebraic, and one function is exponential. I'm writing those two names down because it's very clear that we need to identify which one is it that we're going to let u equal and which one is it we're going to let dv be. So with that information, keep in mind, I'm going to go ahead and let u be one of those functions. I'm going to let dv be the other function. Now keep in mind that dv will again absorb that dx piece. Now, if you look back up at this formula, you'll notice that we need u, which we'll clearly identify. We'll need v, which will identify dv. How is it that we're going to get from dv to v? Well, if I've got dv, that means that that's the derivative of v. So what I really need to do is integrate that function. Again, I need to integrate whatever I pick for dv to get back up to v so I can plug it into this formula. You'll notice again up here I have v, so that piece is going to be taken care of when I identify what my dv is and integrate. And then I need du, so that means that I'm going to need du as well. And how do I get du? Well, if I've identified what u is, I'll take the derivative and get du. So looking at this example, again, du is still going to have a dx attached to it. That means that I'm going to have to pick which one I want to be u and which one I want to be dv. So you'll look at this and you'll think, well, I can pick either one because I know what the derivative of x is and I know what the derivative of dx is. The question then resolves is, do I know what the integral of x is? Do I know what the integral of e to the x is? Now keep in mind when I'm asking these questions, I'm trying to decide how I want to group these two functions. I'm going to have an x, I'm going to have an ex, and then that dx again is always going to be identified as part of my dv. So these two pieces are going to be the pieces that you're pulling from the given integral. These two pieces are the pieces that you're going to have to calculus-wise work towards. So let's go ahead and try and just pick one of the examples. If I were to pick e to the x as u, because I know taking the derivative of e to the x is very simplistic. That means that the derivative of e to the x is e to the x, and I have e to the x dx. Now if I let my dv then be the other piece, keep in mind u dv must be this first original integral. U dv must be the first original integral. So everything in here must be part of this multiplied by this. So that means that if I've picked e to the x for my u, that means that x dx must be my dv. And if that's the case, that means I have to integrate x. And integrating x gives me x squared divided by 2, which again isn't difficult to do. There's technically a plus c here, but we're going to ignore it for the time being, and it'll come in at the end. So once I'm here, the question is then, how do we use this formula? Well, again, the integral of u dv, this, because u is this and v is this, sorry, dv is this. That means that this integral is going to be equal to u, e to the x, times v, x squared over 2, multiplied together, minus, and again, here's your minus, the integral of v to u. So the integral of v, which is x squared over 2, du, which is e to the x dx. Now if you're looking at this problem, you're thinking to yourself, well, wait a second. I thought the goal of this integration was to make it nicer, to pull out a piece of that and then still have something we can integrate at the end. What happened to this problem? Well, we pulled a piece out using the integration by parts, and I got minus an integral that is actually more complicated than the original one. If this happens, and again, this is the reason why I did it in this video, if this happens, it means that we've selected the wrong pieces for integration by parts. So I let the algebraic piece be the dv, and I really should have let that be the algebraic piece first in terms of u, and then I should have picked my exponential as dv. And again, some of you might be able to clearly identify the reason why is because integrating normally will make the problem more complicated, where taking the derivative will make the problem more simple. And that's generally in terms of the algebraic nature. So normally I'm going to try and let my algebraic function be u before I would let my exponential function be u. So very quickly trying to do this exact same problem with a different identification of my functions. My u will now be x. Again, my u will now be x. Therefore, my du is 1 dx. And again, notice how that simplifies. My dv will be the other piece that I didn't select. So e to the x, again, dx. And integrating that is very simplistic in the integration technique, since the integral of e to the x is simply e to the x. So now, when I use this integration by parts, keep in mind this is a formula. This u and this v are nothing more than placeholders. They're not being substituted into the problem anywhere. The problem is being substituted into placeholders for the formula here. And then what we're going to do with that formula is we're going to go ahead and utilize it to write it out here. So the integral of u dv, that's the start, this original integral right here, is equal to the u times v, so x e to the x, minus the integral of v du. So it's going to be e to the x times 1 dx. Which we can look at this and say, hey, this part got integrated minus the integral of, this is nothing more than a very simple integration. And keep in mind, all methods of integration that we're going to do, the intent is for us to make the integral more simple. Again, the intent is to make the integral more simple. Think back to the first video. We said, do you know the integral? Number one. Number two, is it an algebraic manipulation so we can make it more simple and know it? Or number three, is it a u sub, in which case u sub makes the problem more simple. So, integration by parts will allow us to tear a part out of the integral and then leave us with a simple integral to evaluate. So I have x e to the x minus, and the integral of e to the x is e to the x. And then again, like we said before, technically way up here there's some plus c's that occur. In this, there's technically some plus c's that occur. I didn't write them anywhere in here because I knew at the end, when I finish integrating this piece right here, there is going to be a final plus c attached onto it because there's no bounds. And that is the result of that problem. Again, notice, let's recall, we are going to attempt to let u equal to the algebraic functions first and my dv equal to the exponential functions first. This is not the end-all cases. There are numerous other cases, there are numerous other examples in terms of equations. So what we're going to have to do is we're going to have to slowly develop all of the different rules in which what we're going to let u equal versus what we're going to let u dv equal to.